Okay, so this is now the second part of that section 2.1 from Griffiths third edition. And what we are going to be talking about now will be covering from equation 2.7 all the way to equation 2.50. Okay, and what we'll be discussing here, what we call stationary states. So what does that mean? Well, we found the wave function for Schrödinger's equation, well, using the separation variables in that case where the potential energy did not depend on time. So what was the solution? This one. The part that depends on your psi will be determined once we solve the equation, once we are given the potential, and the part that depends on your time is already there. So this is a stationary state, and why? Why this word stationary? You see a dependence on time here, right? But if we look at the probability density, that thing that is very important, that gives us information about the probability of where we are going to find a particle. If we look at the probability density, so the absolute value squared of this, what is going to happen is that time dependence disappears. What is the absolute value squared? The conjugate of the function and the function. What is the conjugate? Well, the psi that depends on your x conjugate and the conjugate of this. What is the conjugate of that? Is the exponential, but now that I minus I becomes plus I. Yeah? So this is this first term. How about the second term? Is just copying what we have above. So it's the psi of x and the exponential with that minus. Well, what is the product of an exponential plus something? Let's say plus 3 and an exponential minus something, minus 3. Well, is exponential plus 3 minus 3 is exponential of 0, and exponential of 0 is 1. Okay, so you see that this guy with this one is just 1. Okay, so you see that this probability density does not depend on time. It's just the absolute value square of the part that depends on your position. So that's why we say that this is a stationary state. What is the consequence of that? Well, if you look at any expectation value, you will see that if the system is prepared, if the system is in one of these stationary states, you will see that any expectation value does not depend on time. Okay? Why? Well, we know how to do. We go for the sandwich, right? So the wave function that depends on x and time, the quantity that we are trying to find the let me just write and then I speak. The quantity that we are trying to find the expectation value, and then the wave function. But we just said above that the part that depends on time, for this reason here, disappears. And so what we have here is the expectation value, but computed only with the part that depends on x. So you see that it does not depend on time. And in particular, if you look at the expectation value of position, what are we going to get? Something that does not depend on time, as we just said above, right? So we will be able to compute it using only the solution from the time independent. So this is not going to be dependent on time. Consequence of that, if we look at the expectation of momentum, right, which is the derivative of the expectation of position, this is going to be 0. Okay, so nothing happens, nothing very interesting happens if we would have the system in a stationary state. So this is the first property that we want to discuss about the stationary states. What is, so that the expectation values do not depend on time, that the probability density does not depend on time. What is the second property that we want to discuss? That these stationary states, they have definite energy, definite total energy. What does that mean? Well, when you learned classical mechanics, you probably learned about this entity called Hamiltonian. And if you haven't heard about it, don't worry, you'll be learning about it. Okay, so what is the Hamiltonian? The Hamiltonian tells us about the total energy of the system. The Hamiltonian, we usually use this letter H. The Hamiltonian is the sum of the kinetic energy plus the potential energy. This is the Hamiltonian in classical mechanics. What happens when we now move to quantum mechanics? The idea is still there. The Hamiltonian is still associated with energy, but we now have, just as we talked about, the momentum became an operator, the position became an operator, the Hamiltonian is also an operator. And I'm putting this hat there for us to remember that we are talking about operators, entities that we work with in quantum mechanics. And what do we have on the right side? Well, momentum is also an operator, right? Which we defined is that h bar over I and the derivative in x. So I'm going to put here this operator squared. That gives me minus, because of the I squared, h bar squared. There is the 2m there. And we have here this derivative. And on the right, the last term is the potential, also as an operator, no? As using their position as an operator. Look how beautiful this is. Look at this. Do you remember when we obtained the time-independent Schrödinger equation? I'm going to write it here again if you don't remember. So the time-independent Schrödinger equation was this. So this is the small psi. Yeah. So this is the time-independent Schrödinger equation that we obtained in the previous lecture. Well, compare the two. What do we see? That we can write the time-independent Schrödinger equation in a very compact and elegant form. How? Hamiltonian acting on our psi gives us energy psi. Okay, so this is a beautiful equation. Not very compact and contains so much information. It has all this within it, right? Okay, so, and this is the equation that we'll be solving in this chapter 2, as I told you. And so let me just write it again. Time-independent Schrödinger equation. And we'll be solving it given a potential. Well, but how does this equation help us understanding what I wrote here, that the stationary states have well-defined total energy? Well, if we were to compute the expectation value of the total energy of our system, how are we going to do that? Expectation value of energy means expectation value of the Hamiltonian, that operator that contains information about energy. And how are we going to compute that? Using that sandwich that we talked about, the sandwich. But remember, we are talking about the stationary states, as we said above here. The part that depends on time gets canceled. So the part that depends on time here disappears. So I can write this with the time, with the function that depends only on x. Okay. All right, good. But now, this part here, what do I have? The operator Hamiltonian acting on this function. just as here. So I can rewrite this as follows. Psi, and here E, psi. Okay, just following the equation that we found. But this E is energy. This E is just a constant that I can take out of the integral. And what survived here is just this part. And this part, due to normalization, has to be 1. So what survives here is this E. Okay, so no wonder we were using this letter E. The expectation value of the Hamiltonian is this E, E from energy. Okay, very good. We found that. But let's do one more step. Now let's look at the expectation value, but not of the Hamiltonian, of the square of the Hamiltonian. I'm thinking about here, about computing the variance of the energy, no, the uncertainty in energy, just as we talk about the uncertainty in position, uncertainty in momentum. So to do that, I need to look at the expectation value of the square of the Hamiltonian. What are we going to get? We do the same procedure. And we are going to be playing with the function that depends on an x. Then we have h squared, the function that depends on x, because of, as we said above, the part in time gives us just 1. Here, I can write this as Hamiltonian operator act on psi. This is E psi, and this E moves away. What survives inside? Well, the other Hamiltonian. And Hamiltonian psi is again E psi. So what we get, E squared and the psi squared dx, which we said has to be 1 for normalization. So we get E squared. Consequence of all that. If we now look at the variance of this Hamiltonian, not trying to find the uncertainty in energy, what are we going to get? This is the variance, okay? We found that for this, the expectation value of Hamiltonian square, we get E squared. Expectation value of Hamiltonian, we get E, is the energy. But because of this square, this is square, this is 0. Okay, so conclusion, there is no certainty in energy. If I measure the energy of a stationary state, I will always get the same value. But this is only true if I am in a stationary state, if I am in a state like this. Okay? So if I measure energy, I will always get the same energy, no uncertainty, no variance is just equal to 0. Okay, so but this is a special property from these stationary states. Okay, third property of these stationary states or the solutions that we obtain, which is very, very important, and you'll be using these over and over again in this course. What is the story? We said that we have to solve the time-independent Schrödinger's equation. First step to then be able to get the solution of the time-dependent Schrödinger's equation, right? Okay, now, you will see that there is not a single solution for this equation. There are, in fact, many solutions, an infinite set of solutions. For the energy E1, I have the solution psi1. For an energy E2, I have the solution psi2, and so on. For you to get a better sense of what I'm saying, suppose we were looking, we are trying to solve this equation, this time-independent Schrödinger equation for the hydrogen atom. what are we going to get? Well, the hydrogen atom, as you know, has many levels. So we would get all of these levels. So that's what we are saying here. There is not just one solution. There are an infinite set of possibilities. Very well. So if there is an infinite set of possibilities for the time-independent Schrödinger equation, for this solution, that means that we have an infinite set of stationary states. We have this stationary state psi1 with the psi1 of x and the exponential of energy 1. We have the psi2 with the psi2 of x and the exponential of the energy 2, and so on. Okay, so we have an infinite set. And more than that, this is a solution of the time-dependent Schrödinger equation. This is another. Psi3 is another. Psi4 is another, and so on. So these are all solutions of the time-dependent Schrödinger equation. And more than that, any linear combination of these solutions will also be a solution. What do I mean? If I pick any of them, for example, if I pick psi1 and I add a constant here and another constant to psi2, so this gave me now a new function. This new function is again a solution of the time-dependent Schrödinger equation. And you can check. You can put this in the time-dependent Schrödinger equation. And you verify that this is indeed satisfied. You just substitute this here. And you will see that since for each one, this is satisfied, for the sum, this is also going to be satisfied. Okay, so you see that we have an infinite number of possibilities. And the most general, solution is this linear combination. Let me put it here, is this linear combination where I have the sum of all the solutions that we have from 1 to infinity. Now, attached to each one, we have a constant, psi n, and that exponential with the corresponding range. Okay? So this is the most general solution for Schrödinger's equation. And we have infinite number of possibilities for these constants. And then you may get horrified and you said, oh, so what is it that we are going to use? And that's the point. How are we going to determine these components and these coefficients, since any would work? Well, this will be determined by the person that is doing the experiment in the lab. The person in the lab will prepare the system in a certain initial state. Okay? Once we know what this specific initial state is, we will then be able to obtain those constants. So for you to get an idea, suppose we have here some plane and the experimentalist will bring some atoms of some quantum particles and put these quantum particles somewhere on the side of this plane. Well, this is the initial state. Okay, with this initial state, we'll be able to get those components and we'll then be able to get the evolution of this state. So the evolution of this state will be given by this whole expression here, will be telling us how these particles will be moving there in time. Okay, so the big point here is we will need to know what the initial state is to finally find what is exactly the solution that will be describing our system. Okay, so this is the end of the second part of this discussion.